We now turn our attention towards the physiology of the kidney and the events that actually take place there, as opposed to just the anatomy of the kidney. And so what we see is that we have basically three processes that are taking place in the kidney. The first is filtration, the second is secretion, and the last is reabsorption. And so if we look at our diagram, then we see each of these three processes depicted. So here we have our afferent arteriole, and here we have the glomerular capillaries, representative, of course, without any of the details. And the glomerular capillaries, as you are aware from our discussions of the anatomy there, are where filtration takes place. And so we see the filtrate moving, the so-called ultrafiltrate moving from the glomerular capillary into Bowman's space. Now there are two other things that can occur then. And so we see the remainder of the blood making its way in the efferent arteriole and then to the peritubular capillaries. So another possibility is this: items that were not filtered but that the body wants to get rid of can be secreted, and we refer to this process as tubular secretion. These items make their way from the blood and into the tubule of the kidney via active transport with specialized proteins. And so toxins, for instance, are oftentimes secreted if they weren't filtered to make sure that they make their way out of the body. The last possibility is this: tubular reabsorption. And so this process, of course, is for items that were filtered but that the body wants to hang on to. And so these items are actively transported back from the ultrafiltrate into the blood. Glucose would be a good example of this. 100% of the glucose that's filtered is reabsorbed via tubular reabsorption back into the blood. So ultimately we see that the amount of a substance that's found in the urine is equal to the amount that's filtered plus the amount that's secreted minus the amount that is reabsorbed. And different products are handled in different ways, and we see depictions of each of these three manners on the screen. So toxins, for instance, like we see here, are filtered to some extent, and then whatever is not filtered is very likely, hopefully, we should say, secreted into the tubule and then leaves the body in the form of urine. As we mentioned previously, glucose is nearly completely reabsorbed. And so we see substance Z here representing glucose. And so we see that some glucose is filtered, but all that glucose in this particular case is transported back into the blood. So in normal circumstances, although there are exceptions that we'll talk about in different pathologies, under normal circumstances, all the glucose is making its way back into the blood and none is lost. Now, other substances are partially reabsorbed. So urea is a good example of that. Urea is filtered. Some of that is reabsorbed, as we see here, and then some of it leaves the body in the urine. And so all these possibilities exist, and depending on the substance and the body's need for that substance, then one of these processes will apply to a particular item that's found in the plasma. We turn our attention now to the forces that bring about this filtration. And these are the Starling forces that we discussed in Chapter 12 in the cardiac system chapter. And let's go over these forces here for just a moment here. So there are some forces that favor filtration. In this particular case, the only force that's favoring filtration is the glomerular capillary blood pressure. And so we see the glomerular capillary blood pressure here at about 60 millimeters of mercury. And so that, of course, is forcing portions of the plasma out through these fairly leaky capillaries. And this is the ultrafiltrate that is constantly leaving the blood there in the kidneys. There are two forces that oppose filtration in this particular case. So one is the fluid pressure that's found in Bowman's space, B subscript BS for Bowman's space. And so that's 15 millimeters of mercury. So that's opposing the movement of fluid from the capillaries into Bowman's space. And so that's, of course, distinctly less than the capillary pressure, as you would imagine, that's pushing blood out. But then the second force that's drawing fluid back in is the osmotic force that's due to protein found in the plasma. Now, you'll remember that under normal circumstances, very little, if any, generally no, proteins that are found in the plasma are being filtered via these capillaries. And so this means that there is an osmotic pressure in the capillaries that's completely absent in Bowman space that's drawing fluid back towards the capillaries. And this is significant, 29 millimeters of mercury. So if we add these together, then what we see is that we have 60 millimeters of mercury favoring filtration, 29 plus 15 opposing it. That gives us a net filtration pressure of 16 millimeters of mercury. That 16 millimeters of mercury creates a significant amount of filtration. The overall glomerular filtration rate in a 154-pound person is about 180 liters per day. 90 bottles of Mountain Dew, the volume that would fit in 90 bottles of Mountain Dew, filters out of the human blood per day. Now, you've noticed you don't excrete 180 liters of urine per day, and you couldn't survive if you were doing that. So nearly all of that is reabsorbed via the processes that we talked about previously and that we'll talk about moving forward here. But ultimately, that's a significant amount of filtering, and so that means that because the average person, 154-pound person for that matter, has a plasma volume of 3 liters, then the total volume of plasma is filtered 60 times per day. Additionally, the glomerular filtration rate can be adjusted by adjusting that pressure. And so it's a fairly simple idea, but there's essentially 4 possibilities for altering that pressure. And they're all depicted on this screen. And so one that we see is we can constrict the afferent arteriole. And if we do that, we of course decrease the pressure, and so we decrease the glomerular filtration rate as indicated by these arrows. We could also constrict the efferent arteriole, which of course increases the filtration pressure and increases the glomerular filtration rate. Third, we could dilate the efferent arteriole, which, as you would imagine, decreases the glomerular pressure and decreases the filtration rate. Lastly, we could dilate the afferent arteriole. And as we dilate the afferent arteriole, then we increase the pressure because we allow more blood to move into that glomerulus. So all of these mechanisms are used by the body to adjust filtration rate depending on the needs of the body at any given time. We turn our attention now briefly to tubular reabsorption. And what we notice is this, that some substances are controlled. In other words, you can modify the amount of tubular reabsorption that's occurring. Other substances are not controlled. For instance, you just reabsorb 100% of that compound all the time. Organic nutrients, for instance, such as glucose. The reabsorption is always high and it's not regulated, which means that you're constantly reabsorbing all or nearly all of that particular compound. Water and ions, on the other hand, are under physiological control. Although, if we look at this table, the reabsorption of water is extremely high. As I mentioned, you notice you don't excrete 180 liters of urine per day. But you do excrete perhaps 1.8 liters per day. And so this would mean that water is 99% reabsorbed. But, as we're going to learn about, the body can adjust that significantly depending on how much water the body is taking in and how much water the body is losing via other avenues. So we also notice that sodium is nearly entirely reabsorbed, 99.2% reabsorbed, but that can also be adjusted in manners that we'll talk about. There we see glucose, which is 100% reabsorbed, as we talked about, and then we see urea, which is a good example of a compound that's under regulation, and so the amount of urea that is absorbed can be adjusted. We now want to talk briefly about how items are reabsorbed. And there are 2 possibilities. One possibility is simply diffusion. Diffusion occurs through tight junctions between epithelial cells. And one thing that we do notice is the following. So water leaves in massive quantities in the proximal convoluted tubule. And as that water leaves, then the concentrations of other compounds, urea being a good example, increase dramatically inside the lumen of the tubule. And so this creates a situation in which you have a high concentration of urea inside the tubule and low concentration outside, and so this encourages diffusion of the of urea, for instance, out of the tubule. That's what that bullet point refers to there. It says concentration increases in the proximal convoluted tubule. Because water is leaving, the concentration of a number of compounds, including urea, increase, and that encourages their diffusion then from the tubule into eventually the peritubular capillaries. The other possibility is mediated transport, and so of course you need a transporter protein for this. This would apply to compounds that are big or of course water soluble and cannot make their way across the membrane on their own. We do notice that cotransport is common in these situations, as you may remember from earlier discussions in our class, and we'll talk about again shortly. We also notice that we have transport maximums, as you are well aware, occurs when you have mediated transport, because the transporter proteins, just like an enzyme, can become saturated. So to illustrate this, let's take a look at the graph on the bottom right-hand side of our screen. And what we see is that we have plasma glucose concentrations found on the x-axis. We have the glucose that is filtered, reabsorbed, or excreted on the y-axis. And so we notice a couple things here. So we start out with a plasma glucose concentration, the blue line that goes up and up and up and up. And normal plasma glucose concentrations are right there in the realm of 150 or so. And so what we notice is that the absolute transport maximum for glucose is around 390. And so the normal levels of glucose in the blood are well below the transport maximum, and the green line represents glucose that's excreted, therefore glucose that appears in the urine. So there is no glucose found in the urine at normal plasma glucose levels. However, in the case of situations such as diabetes, when you have very high levels of glucose in the plasma, if we continue to go up past 150 milligrams of glucose per 100 mils, then eventually we get to a point where we do start to see glucose that's found in the urine. And we get to this point because we eventually reach this transport maximum. And what we see is that once we get to 200, we see an ever so slight decrease start to occur in the amount of glucose that we can reabsorb as a result of the fact that we're getting to the absolute maximum that these transporter proteins can handle. And so as we move up to 300, then we are seeing some significant glucose found in the urine because we're at this particular point on the curve. And then by the time we get to 400, then we're out as far as reabsorption of glucose via these transporters goes. They can't handle any more. So that means that every bit of glucose that appears in the plasma past 400 milligrams per 100 mils is going to show up in the urine. And that's why we have this perfectly linear curve that is found in the excreted glucose once we make our way past, really probably 350 or so, somewhere maybe 370. So that's what we notice as far as glucose goes, that we can saturate those transporter proteins. And this would apply to any compound that utilizes mediated transport for reabsorption in the kidneys. We turn our attention now briefly to tubular secretion. And so in the case of tubular secretion, just like in the case of reabsorption, there are two mechanisms by which this transport can occur. One is diffusion and one is transcellular transport. What we do see in this case, though, is the following. That hydrogen ions and potassium ions are the most significant secreted substances, but many other substances are secreted as well. Chlorine, creatinine, penicillin, numerous other drugs, toxins, pesticides are secreted. And of course, in case we forgot, we want to remind ourselves that secretion is the process from going from the blood, from the peritubular capillaries, in other words, shown in this diagram, back into in this case, the distal convoluted tubule, which is what we're seeing if you follow the pointer right here. And then we get to the collecting duct there. So in this case, you can see those ions making their way from the peritubular capillaries into the lumen via tubular secretion. Not too much of a exciting animation there, but it did show the movement one time. Oftentimes, this is coupled to the reabsorption of sodium, and we will look at the details of this in a moment. You may remember it from our earlier discussions of co-transport, but it's not uncommon for tubular secretion to be coupled to the reabsorption of sodium. In section 14.4, we talk about this interesting method of measuring the glomerular filtration rate. And what we see is that the glomerular filtration rate is equal to the amount of substance that leaves the body in urine that's not secreted or absorbed. So if we had some particular compound that the body only filtered and didn't secrete at all and didn't reabsorb at all, then we could measure the amount of that in the urine, and if we knew the concentration in the plasma, then we could calculate the overall GFR from that data. And interestingly, it's difficult to find such a compound in real life, but inulin is a polysaccharide that's present in some plants that is indeed filtered but not reabsorbed and not secreted. So what we notice is this, that we know the concentration of inulin in the plasma, and this is not insulin, of course, it's inulin, which is this compound in plants. So if you've been consuming plants that contain this, the concentration of it in the plasma is 4 milligrams per liter. If we look at the total amount that's being released from the body in the urine and we see that it's 30 milligrams per hour, then we can very simply divide 30 by 4 and we get 7.5 liters per hour. In other words, to get this 30, then we've got to be filtering 7.5 liters of plasma per hour to end up with our overall 30 milligrams per hour. So in the real world, unfortunately, the interesting aspect here is that inulin is hard to measure, and so we could do it, but it'd be super expensive. And so creatinine is used as an approximation of inulin. There is no reabsorption of creatinine, but there is a little bit of secretion. So it's not perfect, but it is a rough measure of kidney function, and so blood creatinine concentration can be measured and compared to the amount that's found in the urine, and that gives an approximation of kidney function. In section 14.5, we talk about micturition, otherwise known as urination. So the bottom line is that all this filtering process that we've talked about sends, of course, the final remnants of ultrafiltrate, what has not been reabsorbed, and of course what's been added via the process of secretion, down to the bladder. And so the walls of the bladder are composed of smooth muscle that are collectively known as the detrusor muscle. And the detrusor muscle is, of course, relaxed during filling, and then it contracts during micturition. In fact, if we look at our table over here, we'll go ahead and glance at that as we are at this point in the discussion. So the nerves that go to the detrusor muscle are parasympathetic, and during filling, the contraction is inhibited because stimulation of these nerves is inhibited. During micturition, the muscles are stimulated to contract, as you would imagine, and that's what causes emptying of the bladder. Now, you don't just always release urine as a result of two aspects of the bladder or the urethra. So one is the internal urethral sphincter, the other is the external urethral sphincter. So the internal urethral sphincter is found here, and it is closed during filling for two reasons. One is that if we look here, then we see that the internal urethral sphincter is innervated by sympathetic neurons. These are stimulated during filling to contract, and then they're inhibited during urination. But a second reason that the internal urethral sphincter is closed is simply the position that it takes when the detrusor muscle is relaxed. And so there's this compressed area down at the base of the bladder when the walls of the bladder are not contracting. And so that internal urethral sphincter is closed for those two reasons. One is lack of, or one is actual stimulation that's causing the muscles to contract, and another is the position as a result of the relaxed muscle in the remainder of the bladder. Lastly, we have the external urethral sphincter. This is the one that you have conscious control over, and so the external urethral sphincter is stimulated during filling. It's also contracted during filling, as you would imagine, and it's inhibited during micturition or urination. And so this is under somatic control, and so you do have conscious control over this. This is the one that you're taught to control at a very young age, when it was inconvenient for your parents to constantly be cleaning up after you, and it was eventually embarrassing. And so urination then is a result of these three sets of muscles. The smooth muscle in the bladder, called the detrusor muscle, contracts. The internal urethral sphincter, which you do not have control over, relaxes. And the external urethral sphincter, which you do have control over, also relaxes. And this means that urine can leave the body, leave the bladder, and therefore leave the body during the process of urination.